We'll be talking about a multi-species, totally asymmetric zero-range process and Macdonald polynomials.
Okay, thank you, Shrikar. Thanks for the invitation and the introduction. So I'll be talking about some joint work with Mandelshtam, who is at Waterloo, and James Martin, who is at Oxford. And this is a bunch of two papers. This first one has recently been accepted in algebraic combinatorics, the free and open journal. And this has been something just came on the archive a month or so ago. So I'll first motivate why we studied what we studied, and the motivation comes from areas maybe orthogonal to what this audience knows. So I'll spend some time on that. As part of this, I'll give a new combinatorial formula for some Macdonald polynomials and come to the multi-species totally asymmetric range process. As in Nimisha's talk, I'll describe another process that lumps to it, what we call the tableau process. And finally, I'll end with some results for observatories. Okay, so not all of you might be excited about symmetric functions like some of us are, but you know, it's kind of bread and butter of algebraic combinatorics. So let me set some notation. So that x1, x2, x1, x2, etc. Be a family of commutating indeterminates. So you think of them as counterpart number of variables, and you consider symmetric functions, symmetric polynomials in these variables with coefficients in a rational field. And there are several natural bases of this algebra which are indexed by partitions. So the classical ones are monomial symmetric functions, which are the analogs of the monomials. So you take any monomial and you symmetrize it. These are, I mean, the reason we say function instead of polynomial is simply because we are dealing with infinitely many variables. So each polynomial is has infinitely many monomials. Okay, but it encodes. It's encoded by family commutative data. So feel free to ask questions. I can give it. So monomial symmetric functions, elementary, complete homogeneous, partial. These are the four classical ones. And from representation theory comes this short functions, which are kind of the most fundamental objects, and they specialize to many of these. So these are very important. They are the characters of the GLM representation. So they play a very important role. And these Macdonald polynomials are a generalization of them, which were defined originally by Macdonald purely combinatorially, but they sort of just magically appear in all kinds of areas. So you introduce two new parameters, Q and T. You think of them as common variables, and so Macdonald, just without any motivation, kind of defined them. And if you want one motivation, that he showed that simultaneously they generalized many classes of polynomials, short polynomials, polynomial jack polynomials. These were all studied from various different motivations in the literature. Also Whittaker functions, which was studied in number theory. So simultaneously, in one shot, he just generalized all of them. And to define them, I'll define an inner product. So remember, I said that p lambdas, the power sum, they are the basis. So you can define an inner product by defining them on the basis. So here is our formula. So the Q and the T appear here. So it's orthogonal. So the P's are orthogonal with respect to this inner product. The inner product is given. With their norm basically given by norm square. And they are uniquely determined by the following. So P lambda x t q x q t are these polynomials.
Sorry, 1 second.
Yeah.
The last line, what is the small p power symmetric or this p lambda?
Small p lambda is power sum. So they define the basis, and the z lambda is some products of ratios of factorial. So I don't want to write it. It's some explicit quantity, and there is this product of ratios. So Lambda is a partition, so it has, as Nimisha explained, it has finitely many parts. So you take 1 minus q to the lambda I, but take product. Okay. So they are uniquely determined by the following conditions. So they have the, so in terms of m's, the monomial basis, so they have a monomial expansion. So P lambda, capital P lambda, expands in terms of m mu's, where mu is less than or equal to lambda. Where this less than or equal to is a certain order relation on partitions called the dominance order. I can explain it if needed, but for the talk it's not so important. And moreover, the diagonal coefficients are 1, so the largest coefficient is 1, and they are orthogonal with respect to this. Okay, so these are known as the triangularity. This is the triangular relation in normalization, and it's kind of not at all obvious, but true that these determine the polynomials uniquely. So this is a huge overdetermined system of equations, and somehow amazingly they have an exact solution. Okay, so sorry, M was the monomial basis. Monomial symmetry. Do you want, if you want me to give examples, let me.
Actually, examples would be great.
Okay. So if I take M32, let's say, so lambda is 32, let's say. So M32 will be x, you take x1 cubed x2, and then you symmetrize it with respect to x1, x2. So you take x1 cubed x3 plus etc. So x4, etc. So there's that influence. Plus then you'll have 3 do's. And then you'll have x2 cubed x1 squared plus x2 cubed x3 squared plus etc. And then you go on. So in principle, you have this influence. Okay. And then you can define it. So you basically take one monomial and you symmetrize. Just take it symmetric. You can also stop with finitely many variables, but then you will get a genuine polynomial. And now you'll get what's called a symmetric function. So these Macdonald polynomials, if you stare at them, they have quite complicated expressions, and the coefficients, all of these are quite complicated rational functions of Q and T. But in '93, Garcia and Heyman came up with these modified Macdonald polynomials, which are essentially equivalent. They do a certain plethysm, certain operation, which is like a composition of representations. But let's not go there. This is just certain transformation. And then they are uniquely determined by some other set of axioms, and this is just reformulating. And I don't want to explain too much of the notation. This box bracket, the square bracket is essentially indicates plethysm. So this is now an expansion in terms of Schur's, and there's some complicated conditions related to dominance order. But again, it's not at all obvious that these are unique, but they do. And here the nice thing about the modified Macdonald polynomials is that when you expand them in terms of Schur's, you will get, or even monomials, you will get only integers, integer valued polynomials in Q and T as well. So they're nice. So there's a lot of literature on these, but let me just go through the things relevant for us. So in 2005, in a very influential paper, Arvind Ayer gave a very nice combinatorial formula for this modified Macdonald polynomials. They summed over certain tableau, and they had two statistics corresponding to the two variables Q and independently. So Corteel, Mandelshtam, and Williams, they built on some earlier work of continuity and Miller, and they gave a combinatorial formula for these P lambdas, the original Macdonald polynomials, in terms of these multi-line Qs that Nimisha explained, and which were, as she said, they used in describing the stationary distribution of the multi-species ASEP. And Corteel, Mandelshtam, and Williams, along with Haglund and Mason, they did a combinatorial formula for these P lambdas, the original Macdonald polynomials, in terms of these multi-line Qs that Nimisha explained, and which were, as she said, they used in describing the stationary distribution of the multi-species ASEP. And Corteel, Mandelshtam, and Williams, along with they gave a formula for H tilde, the same thing as earlier, but with fewer terms. So this paper is important because they gave a certain conjecture. And in a completely separate department, Garbali and Wheeler said they used theory of integrable systems to give another completely different. So in this paper above, CHMMW, they conjectured another formula for H tilde lambda in terms of match, the major index statistic. So match is major index and in is inversions. And a new statistic, we will call it Quinn, and I'll explain. So in our first paper, we settled this one. The second is a more kind of philosophical question. So the objects, the multi-line queues used for describing the multi-species ASEP could be used to compute the stationary distribution. So the multi-line queues could be used to compute the stationary distribution of the multi-species ASEP. And the question was, is there another interacting particle system which corresponds to H tilde? So the Macdonald polynomials were useful for ASEP. Is there something else for which the modified Macdonald polynomials? And we will show that there's a zero range, multi-species zero range process, which works. Okay, so let me set some notation. So as usual, lambda is a partition usually decreasing order. Now there's unfortunately yet another notation for partitions. It's not in a diagram. Don't blame me, and this is in the literature. So this is called the diagram, and this is read column-wise. So lambda I is the ith column. Lambda I is the number of boxes in the ith column from the left and bottom left. Okay, so this is 352. And fillings or tableau are the
It should be decreasing.
Yes, right, should. Yeah. And the filling is just a tableau or filling of the cells with arbitrary integers, no restriction. So there's no weakling, phasing, decreasing. So you just fill them with arbitrary integers. And if you restrict the maximum n, maximum integer that can be filled, then we call the set of all such tableau. And so the monomial weight of such a tableau is just the product of xi to the number of times I appears. So that's denoted x to the sigma. So x1 appears 5 times, so this x1 to the 5 and so on. Naturally. So you'll have a product of xi to the power. Okay, so now let me define the major index. Okay, so in any tableau, like in this example, you can have a descent in which a larger entry below a larger entry is a smaller. So this 3,1 forms a descent, this 3,1 forms a descent. And for any cell, the leg of the cell is the number of cells above it in the same column. So it's unfortunate notation. It sounds like your leg is all the way up, but that's again not my fault. So then the major index is the sum over all the descents and of 1 plus the leg. So in this example, let me just explain the example. So this 3 is a descent because 1 is smaller than it, below it. So you get contribution of 1 from this. You get a contribution of 2 from this 3 because there are 2 cells above it, including itself, and then 1 and 1. So 1, 2, 1, 1 gives. That's it. Okay, so there's another statistic which is the in, which is much more complicated. I'm not going to define it. I'll do something very similar. So this in this influential paper, so Arvind Ayer showed that H tilde lambda can be written as a sum over all tableau of this shape lambda, or all tableau sigma of shape lambda, this kind of diagonal representation, where you take x to the sigma, q to the match of sigma. So yeah, I admit I'm not explaining in, but the spirit is, I hope it's clear. So note that you can fill it with arbitrary integers. So you can get as high integers in any cell as you like, and so it's a miracle that you get first of all a symmetric function after all of this, because the statistics are very complicated. And moreover, that so
But you somehow understand by the largest table you can give the n that. So for the tableau you had whatever 3 is the highest you can give.
no, just this example, I could have put 24. I can put anything.
Oh, I see.
So if I maybe it's not a good example, but it's a coincidence that the height of this is 3 and the maximum actually is 1.
I meant that the type lambda n means n is the.
Yes, but I'm not put n over there. So this is over all sigma. So you take everything possible. So if 24 appears, you'll have x24 to the number of n. So
Admittedly, we don't know what is the n, but if I just compute match, then I actually do not care. I mean, it's basically relative information that is required, right? So n can be very large.
yes,
But if the lambda, if the sigma is a specific type of a tableau, then large number of changes cannot be. It's only relative information, which is less, which is more.
correct.
These
That's
are
it.
the two are the same.
Right. So that's sort of the point. And also for the in also it will turn out that the relative numbers are in the
I have some very basic. There you mentioned some other models of polynomials, right? But these have only 2 parameters, Q and T.
yeah. The other ones had only one parameter.
Yeah, but there were some 3 different. They were already related already. I mean, the Schur, the Littlewood, and the Jack polynomial.
So Schur doesn't have any extra parameters. All Littlewood has a T.
As a
Jack is a complicated limit. So the Macdonald polynomial at Q equal to T becomes the Schur polynomial. They just disappear. But if you take Q going to T, if you set Q equals T to the alpha and take T to 1, then the alpha survives and then you get the Jack polynomials. These appear in completely different contexts, I should say. So it's really amazing that Macdonald unified all of them in one shot. And he had posed several conjectures about this, which were solved by Charad. Anyway, okay, so I'll come to our statistic, which we call a Q inversion. So this is at the same level of difficulty as in. So I thought it's better not to overload the audience. So look at 3 cells. So you have this diagram. So it's this complicated thing. And you have these 3 cells where one is directly below the other, and the third one is anywhere to its right, okay, to the right of the cell. So that's and now we say that these form an L triple because it looks like an L. And there's a degenerate notion of this is if V and W are in the top row, so they are like this. So if they are over here. So this is V. So and the U does not exist. So that's also a degenerate. Is there a question?
No. It's CD, which is not understanding what you're saying.
Okay. It doesn't understand Desi accents. Yes. Okay. So we say that these form a Q inversion if these 3 entries, as you read counterclockwise, are increasing. And if there are ties, that's broken by a certain reading order, which I mean, it's already quite difficult. So, for example, 1, 2, and 3 form a Q inversion because as you read counterclockwise, you first see a 1, then you, at some point, you first see a 1, 2, 3. It could also be like this 1, 2, 3. And for the ties, it turns out that things like 1, 1, 2 also form a Q inversion. And the opposite ones. So as you read 3 numbers in a circle, 3 distinct numbers, there's only one way that they can increase. either clockwise or counterclockwise. If they are increasing counterclockwise, then you form an inversion. Q inversion. And if you have just these two on top, then if they are in increasing order, then you say that. So for this running example, let's look at, so I should not have highlighted this, but if you look at 3, 1, that there's nothing on this row that gives you a Q inversion. If I look at 2, 3, this 1, 2, 3 gives a Q inversion. So that's this one. And quin of sigma is the number of Q inversions. Okay, so this is the level of complication. So it's really nice.
So previous slide, the Q inversion definition was sigma. What is the inversion?
If the entries in it increase as we go counterclockwise. So
W can be very far also.
Yes, arbitrarily far. So I mean, it's a miracle. So I should say, in was very similar to this, and this idea is borrowed from.
The order has to be preserved within the, sorry, the B to W order has to be preserved.
Yes, for the degenerate case, or in this case.
Can you put the example?
Yeah. So if you look at this 1, 2, then look at this 3.
Is it okay?
That's the 2.
Oh, I see. Because in between there are 1 and 2, but
It doesn't matter. You look at U, V, and W only and forget everything.
1, 2, 2, 1. Is it?
Sorry?
1, 2, 2. That's not a Q inversion.
No, that's not. But I don't want to explain why. I can. Actually, 1, 1, 2 is okay. 1, 2 is also okay.
What is it you have marked as red here in the board?
This 4 corresponds to this with UV, and the W's are this 2, 2, 3, 3. So, I should have given this.
so this was the type, the reading.
Yes, this is the. I can explain it. This. Okay, so the total number of Q inversions is 12. And quin of sigma is the number of Q inversions, and you might ask why quin, and this because this multi-line Q's, that Q will come in. No. Sorry to disappoint.
But what is the breakup you have done here? What is the 0?
I broke it. So this I broke it up by UV pairs. So first UV is this one, then the next UV is this one, then this UV. I mean, one can break it up in UV. Most. So in our first paper, we proved that the modified Macdonald polynomial is given by Q to the match and T to the quin. So Arvind Ayer ruler had T to the in, which is a very similar but different statistic, but also turns out to be the case. And I should just say that it's not at all obvious to go from one to the other. So that's what I'm saying, and we do not think. So here's an example. So I look at lambda 2, 1, 1, and I just focus on 2 variables. That's again, this is a coincidence. In could have been 3, but I want a reasonable example. So if all of them are 1, then I get Q to the 0, T to the 0. So these give monomial weight x1 to the 4 and x2 to the 4 respectively, and you can see that they are symmetric. And then if I look at x1 cubed, x2, I get these 4 tableaux. So I have to fill with 3 1s and 1 2, and these are the 4 ways I can do it. And if I fill with 1 1 and 3 2s, then I get these 4, and you will see that the sum of these 2 are the same. So that's the miracle ring. That's why the symmetry is. And if I take x1 squared, x2 squared, therefore choose to 6. So let me explain just this. I have Q to the 1 because there's 1 descent. So means that index is 1, so that used to be 1. The T to the 0 is simply because there's just no Q. And if you sum all of these, you get the same. So I will leave that in what follows. So let me recall what zero range processes are. So they are first defined by Spitzer again. And we'll think of them in continuous time. And you can in principle define them on arbitrary graphs. You might have to give some other data like sinks. We will again consider the ring with n sides. So the n sides, the first and the last identified. And in its simplest formulation, there are just k indistinguishable particles. So all particles are the same. And now any configuration is, so there's no restriction, unlike the asymmetric exclusion process, there's no restriction on the number of times, number of particles at a given site. So tau, if you have n sides, so tau 1 to tau n is any allocation of particles. So this is just a weak composition. So it's just a integer vector. Okay, no negative integer. And we will move particles clockwise. So suppose f is any function from the non-negative integers to the positive reals such that f0 is 0. Then a particle jumps from side j to j plus 1, not this one, mod n, with rate f depending on tau I. How many particles there are at the given site. Okay, so if you have, so from here to here, let's say clockwise. So let's look at this way. So this particle will go from here to here with rate f3, and this will move from here to here with rate f2, like that. Okay, so it only depends on the number of particles at that site. So that's why it's called zero range. It does not depend on anything other than the local information on that site. So the rate only depends on the information.
It's not increasing or
Nothing. In principle, it can be anything. So what Spitzer proved is that the stationary distribution is always a product measure, no matter what f you take.
So on general graphs, the issues of conservation of the particles, somehow you have to ensure the particles
Yeah, no, you can, right. So at this level, you always have conservation. So,
right.
Yeah. So we will, if you have addition or removal of particles, then one has to change. This setting is not as big. But here, with full generality, any f, there exists a g, so then the stationary probability of g is tau is proportional to the product of the g tau. It's really amazing result. So this is the same paper where we introduced the ASEP. That's just a remarkable. Okay, so now you have the single species zero range process. You could introduce multiple species, just like is done for the ASEP. But now the question is, what are the rates? So there are many variants that have been studied. So going by the Japanese group, and in different papers there are different collaborators, and they studied many variants. You can say multiple particles can jump. You can say one particle can jump. The dependence of the rates. So all of these, so they are motivated by integrability. So all the things are integral and there is properties, certain nice properties. But so we started working on this and we found a model, and then much later we discovered that this was already studied by Takayama in this archive paper. As far as we know, he has not published it. It's still not there. I mean, it's a nice paper. I don't know why it was not. Anyway, so there are these. So you fix a partition now. So we will think of the partition as the content of the system. So if lambda 1 is 3, then that means there is a particle of type 3, and so on. Okay. So in particular, we can write lambda in frequency notation as 1 to the m1, 2 to the m2, and so on. So there are m1 1s, m2 2s, and so on. That's sort of like what we had, and the sum is k. So the total number of k particles, and we have n size. And now you can have any number of particles of any type at any size. So each configuration is what we call a multi-set combination of type lambda and part. So, or if you take 2 1 1 as the partition and 2 sides, then these are all the 6 possibilities. So all the 2 1s can be on the first side or on the last side, or they can be split in any way that you like. But the 2 1s are indistinguishable. So that's clear. And now I'm going to define the Markov process.
Can you go back to?
Yeah.
be?
Lambda is the particle content. So there's 1, 2, and 2 ones. So I could have 1, 1, 1, 1, 1, in which case I only have, that's the single species. Or I could have n minus 1 up to 1, in which case I have 1 of each. Okay. So now so I define R multi-species phasor, totally asymmetric zero-range process. So every transition will consist of a single particle jumping from side j to j plus 1. And we will think of the lower particles being weaker than higher particles. I'll explain what weaker is. So we have one global parameter t, which I would prefer to think of as as a real number less than 1. And side dependent parameters x1 and x2. Okay? So for each side j and each integer, each positive integer, I have an exponential clock of index a at side j, which rings with rate t to the a minus 1 divided by x2. Okay? So when this clock rings, if the side contains less than 8 particles, nothing happens. Otherwise, the ath highest particle from top jumps to side j. So let me explain with the result. So lambda is 3, 1, 1. Let's say we have 3 sides, and we start with this configuration: empty, 3, 1, 1, empty. Then so all the rates are going to be proportional to xj inverse. So in this case, x2 inverse will come. So the highest particle is 3. So 3 will jump to the right with rate x2 inverse t to the 0, because a t to the a minus 1, a is the highest, let's say eighth highest particle. And now there are 2 ones. So each of the 1 can jump with so you can assign t by x2 inverse t to this guy and x2 inverse t squared, but they're indistinguishable. So the rate for this will be x2 inverse t plus t squared. So in other words, you will have, so if you have from the jth side, you have, I don't know, some things. So you have a1, a2, a3, a4. So this first guy will jump with rate, so there's always a 1 by xj, and then I'll have t to the 0 here. This guy will jump to t to the 1, and this guy will jump to t to the 2, and this guy will jump to t to the 3 times this. But if they are equal, then if any two are equal, they will add. So that's what this t plus t squared is going to. And similarly from this one, 1, 3, empty 1, 3, 1, the 3 can jump right with rate 1 by x3. It's on a circle, remember, so the 3 will go over there. For the 1, this 1 can jump to the right with t by x3. And here there's a single 1, so it will jump right with, come here with rate 1 by x2. Okay, so that's the idea. So for this example, the stationary, so if you compute the stationary distribution explicitly, you have this nice formulas. So, and the denominator turns out to be exactly, which is the lowest common denominator, which makes it from the distribution, turns out exactly to be the modified Macdonald polynomial with this partition. These two variables x and x2, q equal to 1. There's no q, remember, it's just q. So it turns out that q equal to 1. Okay, so there's something nice going on. So the partition function, so if I think of the stationary weights as polynomials in x1, x2, and so on and t, then the partition function is the sum of these, and our main result, or our main result is that the partition function is precisely the modified.
The f doesn't play a role.
What is f?
The rate of process will jump.
No, the rates are precisely this. So the f is this. But don't compare with that, because that theorem only holds for single species, and Spitzer's result only holds with this one type. So there's no canonical way of describing multiples. So we found independently, and notice that Takayama had already done it. That this is a nice choice of rates. But he He did not know the connection to the modified method. Yes. And so Q equal to 1 is
Just right there in front of you that if this particular choice of the rate will actually
no. Sorry, maybe we tried some small examples. First, played around with some small examples.
A single species, these kind of, I mean, there is only one. In single species,
Yes, so that will correspond to the partition 1, 1, 1, 1.
Was this already?
It was not studied, but it I mean, so no one had noticed that case corresponds to this, but okay, it's not difficult. So the remarkable thing is that this guy is a symmetric function in this one. So on the ring, you're only guaranteed symmetry up to rotation, right? You can, if you change xi to xi plus 1 mod n, then you should get symmetry. But here, this guy is actually symmetric. It says full symmetry. So that's another miracle. Okay, so let me recall the Q series notation. So the Q numbers are, if you have not seen this before, these are analogs of the integers. These are very natural in various contexts. So the nth Q numbers, 1 minus Q to the n by 1 minus Q, 1 plus Q. So, and you can define a Q factorial by taking the products of these things. Q factorial is the product of the first n of these Q numbers. And there's you can define the Q binomial coefficient, which is the natural thing. And choose k is Q factorial of n divided by Q factorial of k factorial of n minus k. And it's not immediately obvious that this is a polynomial. I mean, it's not difficult to see that n choose k is an integer, but it's not as easy to see that this is but okay. And then one can define the Q multinomial coefficient, and this is also so if you have a tuple of integers alpha 1 for alpha n, you take the Q version, Q factorial of their sum, and divide by the division. Okay, so the reason I introduced this is to say, give you some properties of H theta. Yes. So, so at Q equal to 1, something special happens. The modified Macdonald polynomial for arbitrary lambda factors into a bunch of modified Macdonald polynomials where the partition is a single one. Where the ones is the number of ones depends on the conjugate partition. And if you have just a bunch of ones, there is a sum. You can write it as a sum of monomial symmetric functions. With the coefficient, which is the multinomial coefficient, T multinomial coefficient. That is the same thing as before with Q replaced by T. And so, for example, if I take 2, 1, 1, my running example, then it factors into H tilde of Q. Okay, so let us make one sanity check. So I said that I've said here that if I look at the multi-species tracer on n sides with content given by lambda, I get this partition function. But as I think someone pointed out, from the point of view of the multi-species tracer, only relative order matters. So if the rates only depend on the relative order of particles at a given set. Because once I order them from top to bottom, the first one will go with rate 1, and then T, and T squared, and so on. So only the relative order of particles matter. So if I look at a tracer, I look at a tracer where there are 3 particles of types 1, 2, and 3 respectively. This is the same as having, I don't know, 2, 17, and 23. And how does it matter what the labels are? But the corresponding partitions are very, very different, and therefore they have very different H tildes. Right? So the polynomials are very different. In fact, this will have like a massive. So for this result to be true, we would need at least that the modified Macdonald polynomial indexed by 21723 to be divisible by the one indexed by 321. And that indeed turns out to be the case. So one sanity check is done. And to give an idea of the proof of our theorem, we can again use multi-line queues, similar to what Visha mentioned. But we will, so we can construct a multi-line zero-range process on a cylinder. So at each level you have a zero-range process, and they are coupled. We can couple that. But we can get something even bigger. We can get a Markov chain, which is even more enriched, and these are on tableau of shape. So, so this tableau process is quite complicated for general partitions. But if you have distinct parts, this is not so hard. So I'm sort of running short of time, but okay. So I'll describe a process on Tableau that lumps to this. Okay, that's okay. So suppose lambda is a strict partition. So I'm only now talking about strict partitions, just for simplicity. So suppose U is a cell, then south of U is the cell directly below it, if it exists. And now I'm going to define a map from the set of Tableau to itself. So, which depends on which is indexed by the cell, by given cell. So suppose sigma is a tableau with entries 1 through n. So here the n is fixed because we have only n sides, so we have x1 through xn only. So if sigma is a tableau such that the sigma of south, the cell below u has the same content as u, then it acts as the identity. Otherwise, you look above u in the same column and look at the sequence of cells for which the entries are consecutively increasing by 1 mod n. And for that particular chain, we will increment every cell by 1 and leave the others unchanged. So maybe it's good to do an example. So suppose here is a tableau of shape 3, 2, 1. And maximum entry 3. So let me look at the 1, 1 cell, which is this one. So the cell immediately above it is a 2, which is increased by 1. The cell immediately above that is not 3. So the largest contiguous chain is 1, 2, and sorry, I should start here. So look at the 1, 1 cell. This is 3, and I increase mod 3 to get 1. So and I increase. The next cell above is not a 2, so the maximal chain is this, and then I increment by 1 mod n. So just that chain. So with respect to the 1, 1 cell, I get everything is. So it's quite a complicated thing to do. And I remember I also need the t parameter. So to define that, I will need the rotation of upper and lower arms. So you fix a cell. Its lower arm is the set of all cells to its left in the same row and to its right in the row below. And the upper arm is the set of all cells in the row above to its left and cells in the same row to its right. And for every cell U for which the content of the cell is not equal to the content of the cell below, provided with this. So down of sigma U is the set of all cells in the lower arm which have the same content as U. And to every such cell, we will assign exponential clock with rate t to the number of elements in this lower and down fellow, divided by 1 by x of times 1 by x of sigma of U. That's the content. So whenever the clock at this side rings, we will make a transition to RUF. So many times this will act as the identity, but sometimes it will go to another tableau with the same fields. And I've defined, so you might wonder why I defined the upper arm. So I defined the upper arm because there is the time reversed process turns out to involve the upper arm. So coming back to our example, so this one was initiated at site 3, so it was 1 by x. I mean, this site 1, 1, which has content 3, so this was 1 by x3. There is nothing in the lower arm which has content 3 because there is nothing to its left and then nothing to the row below it. And so our theorem is that the stationary weight of any filling or any tableau in this process is exactly t to the twin, is proportional to t to the twin and x. Okay, so as a corollary, the partition function of this process is precisely the modified Macdonald polynomial at q equal to 1 because we don't have a q to the match. And now to complete the proof, I have to show you how the lumping happens. Okay, so maybe in the interest of time, I will skip the two main combinatorial numbers. Let me show you how the lumping happens. So now I have to show you how to get from this tableau process to the multi-species tensor. And here's the formal definition, but maybe it's better to look at an example. So you look at, so let's take lambda as 2, 1, 1 with 3 sides. And now I'm looking at all the configurations that map to this state, the multi-species tensor with this content and 3 sides. So let's look at empty 2, 1, and 1. So how am I going to do that? So I look at the bottommost row. So there are 6 tableaux. So look at the entries in the bottommost row. So the height of a given column will tell you. This is very good. So this column has height 1 and is filled by 3. So there's a 1 in position. This column has height 1 and is filled by 2. So there's a 1 in position. Like that. And this column has height, this is a bad example. This column has height 1 is filled by 2 and then is height 2 filled by 2 and therefore goes to 2. Okay, so that's a bit complicated. But what this says is that the bottom row, the first entry of the bottom row has to be a 2, and the other two have to be a 2 or a 3 because the first side is empty. And the top cells can be filled by anything. Okay, so there's no restriction. So all of these lump to this. And so therefore, to get the stationary probability of any state in the multi-species tensor, you have to sum over all things that project to it, all tableaux that project to it, and take t to the twin. So that's and therefore that shows the partition. And to show this lumping, we have to show that this projection is compatible with the.
How many configurations get the same project back to the same one?
So if you have strict partitions, this is sort of easy because
Yeah, it is known, right?
yeah, it's an explicit formula. Because what we are doing is so if the partition is strict, let's say, then you are filling the your state determines the bottom entries, and all the others can be filled with one throw in. Right? So the number is just a power of n. Okay. So this was the case for 2, 1, 1. So these are the 4 tableaux, and these are their weights, and this lead. If you sum it, this leads to this sum. And if I go back here, this is exactly this sum. Okay. So in the last 5 minutes. 4 minutes? 4? Okay. So let me just tell you one really nice result about symmetry and stop. So these are about local correlation. So suppose we consider the Tazer lambda with Tazer multi-species Tazer with content lambda on the insides. And you now look at the first L sites. Okay, just focus on the first L sites and you fix some configuration there in the first L sites. So let W be a configuration of type mu on just on the first L sites. You fix this in advance. And you want to know what is the stationary probability of having this content W in the first L sites. So we'll consider two related correlations. One is having exactly content W1 through WL, and one is having at least W1 to WL on these first L sites. Okay. So I denote by W bar and W9. These are of course related closely. So for example, if I take lambda to be 2, 2, 1, 1 in this 4, and I look at the first two sites and I demand that the first W is 1 and 1. Then in the first case, I only want a 1 and a 1 in the first two sites respectively. So the 2's have to go in the last two sites and they can go in these ways. And these also contribute to the other case, but in the other case, you can also have 2's sitting in the first site. So you allow everything. And so our theorem is that the probability of observing this configuration in both cases is symmetric in the variables xl plus 1 through xl, the last insight. Okay, so for any L and any content W, these are symmetric polynomials, symmetric functions in the last instance. And we have not seen any result of this type. And the proof is highly non-trivial. It uses some bunch of polynomials. So in this example, one can easily show that this is symmetric in X trillion space. And there is an even stronger symmetry at t equal to 0. So if t is 0, none of these transitions can happen. Only the topmost guy at every site can make a transition. And in this case, also one can show that it's reducible, and the partition function is also it's a H lambda, complete homogeneous. In this case, actually, if you start with so now suppose you start from any initial condition where the first L sites are empty. So the other sites can be filled with anything in any way, but the first L sites are empty. Then at any positive time, the probabilities of observing this W will be a symmetric function of XL plus 1. So this is not only at stationary, this is true at all. And this uses some interchangeability results from Q's. This is earlier work done by James Martin with Balaji Prabhakar. Okay, so I think I'm almost out of time. So I could give some explicit formulas for the density and currents. Thank you for your